Okay, so we are going to take some notes on vector operations in 2 dimensions. Now, I know that you already have a copy of these notes online, all filled out, but I figured I would give a walkthrough of the notes, so as if you were in class. So this might be something you might still want to do on a line sheet of paper, even though you have provided to you the note sheet all filled out. Might just help you to understand the content or the material a little bit better. Also, at the end of these notes, I'm going to go over the first practice problem on the little half sheet of questions that we had. So if you wanted to see a walkthrough of that, then you're more than welcome to fast forward toward the end of the video to watch that walkthrough. All right, so we have vector operations in 2 dimensions. So like projectile motion, so the motion of moving objects up in the air. There's a lot of other things aside from projectiles that have 2 components to them or that have motion in both the x and y direction. So a quick refresher, x stands for horizontal. And horizontal is anything, if we're describing horizontal motion, it could mean east or west, or left and right. So anything that would be around or on that x-axis plane. So back and forth, left, right, east, west. And then y is vertical. So that's up or down, north or south. So moving up and down, north and south in the y direction on our axes. So anything that is a vector quantity can have 2-dimensional motion with it. So displacement, which is what we're going to be looking at today, is 2-dimensional motion. So far we've been looking at 1-dimensional displacement. So if I go north 10 meters and then south 10 meters and then north 5 meters, your displacement would be 5 north. That's what we've done so far, so 1D motion. So now we're going to look at 2D motion, so combining an x and y component. Velocity is a vector quantity too, so we can solve for vector velocity as 2-dimensional speed. And then forces, which we'll be doing soon here within the next week or two. We'll be revisiting this when we look at forces in 2 dimensions. And what we're going to end up doing here is really making triangles. So something is going to move horizontally, and then it's going to move vertically, and it's going to stop. And so then my job is to figure out the displacement from where I started to where I ended. And so to do that, I'm going to make a triangle, and my shortest distance between 2 points, straight line from here to here, is going to be the hypotenuse of my triangle. So I can use Pythagorean theorem, a squared plus b squared equals c squared, to figure out that value for c, or in this case, the hypotenuse of the triangle I made. That's going to represent displacement, or in this example, it's representing velocity. So maybe a duck is flying this way and a gust of wind pushes it north. What's the resultant velocity and angle? So refresher though, if I'm using Pythagorean theorem and I'm just looking for the value of c, so that's set up to solve for c squared. So I do need to square root c on both sides. So we do end up getting that c is going to be the square root of a squared plus b squared underneath all on the edge. So when something moves in 2 dimensions, if we combine both dimensions, it's going to have some sort of angle with it. Now with our projectile units, your calculator does need to be in degree mode. And so for this unit too, calculator should be in degree mode too whenever we're solving these problems. So angles are recorded in degrees. So we want our calculator in degree and not radian. So if you have a calculator like this at home, You hit that DRG button. You want to make sure degree is underlined. And if you have one of those fancier ones that has a mode button around the same spot too, and same thing, hit the mode button and make sure degree is highlighted. If radian's highlighted, then we just want to scroll over and highlight degree there. So when I'm solving for the angle of a resultant vector, I have theta here that's going to represent an angle. That's equal to the tan -1 of the opposite leg over the adjacent leg of my triangle, what we call the inverse tan button. So on your calculator, wherever your tan button is, you'll see in the background your inverse tan, that tan -1 sign. So you'll hit that second button to get that to pop up in your calculator. And then in there is where you'll record your angle. The opposite leg over the adjacent leg. So remember in our triangles, so I look to find my angle. The opposite leg is what's across from the angle. And the adjacent leg is what's next to the angle. All right, so I have a pirate walks 49 meters north and then turns and walks 7.50 meters east. What was his displacement and the angle of displacement? So for these problems, it is always in our best interest to draw a picture. So that's going to give us a visual of the triangle, what's the opposite and adjacent leg, better idea of how the thing is moving. So we have these little picture boxes for this unit. So I'm going to pick a place for my pirate to start. So let's say here. Goes 45 or 49 meters north first. So I'm going to draw an arrow pointing up for north. Sorry, that's a little crooked here, just where I'm sitting. So 49.0 meters north. And then turns and walks 7.5 meters east. So I'm going to connect my vectors tip to tail to show they went north first and then east. And then I'm going to draw that vector arrow pointing in the eastward direction. So he goes north and east and then stops. And so I want to figure out displacement. So when I'm drawing the vector arrow for displacement, I see where do I start, and then I point at where I ended. And so I draw that arrow going from the tail is where I started, and then the tip of the arrow points to where I ended. So I'm trying to figure out how far it is from here to here. I'm also trying to figure out what this angle is here. So to solve for this, I'm going to write out, of course, my givens, what I have. So I have two distance values. I want to think of what direction they are. So dy, distance in the y direction, is going to be my pirate goes 49 meters north, so y. So that's north is a vertical or y direction. And then turns and walks 7.5 meters east. So east, that is a horizontal or an x direction. So that's going to represent my dx. So d for the distance traveled, that subscript x for the direction. Now, when I do that, now is going to be a good time too for me to identify what the adjacent and the opposite leg of this triangle that I made for. That'll help me with the angle problems. So here's my angle. 49 touches the angle. It's next to the angle. So that is the adjacent leg. And then 7.5 is directly across. It's opposite, doesn't touch the angle. So that's the opposite leg. I'll need that for my angle of displacement. Unknown, so we're looking for the total displacement, so just d. And then we're also looking for theta, the angle. I got a couple equations for that. So I can use my Pythagorean theorem. So d is equal to dx squared plus dy squared. So dx and dy squared are representing a and b in my triangle legs. And then to find theta, the inverse tan of the opposite leg over the adjacent leg. It's supposed to be leg there. Here we go. All right, so sub and solve. So D is equal to the square root of 7.5 meters squared plus 49.0 meters squared. So when we put that in our calculator, we should be getting 49.6 meters. Remember, these have to be squared underneath. You got to add them, and then you got to take a big old square root. So double check all of those parts as you're plugging them in your calculator, hopefully, at home. All right, and then trying to find theta here. So I can take the inverse tan of the opposite leg, which is 7.5 meters, over the adjacent leg, 49.0 meters. And so for that, should get 8.70 degrees. And then we also want to designate in what direction. So this case, if I'm treating this as an axis here, I can say that I'm heading in the northeastward direction. You could also word this as 8.7 degrees east of north. Whatever way you feel more comfortable is fine. If you're having a hard time with the inverse tan, usually have a lot of people that like to have me put that in the calculator. So you're gonna hit the second and then inverse tan button, and that's gonna pop up. And then you're just gonna divide within the parentheses. So 7.5 divided by 49, close. That's where we get, oops, I'm sorry. And that's where we get our 8.7 there. So second, inverse tan, and then just type in 7.5 divided by 49. All right, so that's our first practice problem. On the back here, so we have a daredevil tightrope walker is climbing a cable from one building that is 51 meters high to the building across the road that is 91 meters high. The displacement between the buildings is 25 meters. Find the resultant displacement and the angle of displacement. They're going to draw a picture here. So I have two buildings. One that is 51 meters high. And then I have another one that's 91 meters high. So I have this tightrope walker that starts on the 51 meter tall building. And it says the horizontal displacement of the tightrope walker is 25 meters. So the horizontal displacement this way is 25 meters. Now I need to figure out what the distance is from here to here, since my tightrope walker is going up from here to the top here. So I'm not given though what exactly this height here is, but I do know what the height of these two buildings are. So a quick little subtraction can help me out. So 91 meters minus 51 meters, so I can find the difference between the two. That's 40 meters. So this little bit here that he goes up in the vertical direction with is a 40 meter distance. And this one here, the problem says that it's 25 meters horizontally or across. So I want to figure out theta, and I want to figure out d then. So how far is it from here to here, the top of the building? So distinguishing the two x and y components. So horizontal distance, that's x. And so that's our 25 meters. This is next to the angle. So this is going to be the adjacent side. And then dy, so the vertical component that's traveled. And so we subtracted and found that to be 40 meters. That's going to be the opposite leg because it's across from my angle. Looking for a resultant displacement and angle of displacement. So what is just d, what is theta? And so we have our Pythagorean theorem, dx squared plus dy squared over the square root. And then we have our inverse tan of the opposite over adjacent leg. So let's solve for displacement first. So displacement is the square root of 25 squared, meters, plus 40 meters squared. So 25 squared plus 40 squared, take the square root of that. Should be getting 47 meters there at home. So we're hitting second. There's your square root button. And 25 squared plus 40 squared. So 47. And then inverse tan of the opposite leg. So 40 meters over the adjacent leg. And so we get for that one, should be 58 degrees. And so it's good to say, directions. So we could say 58 degrees if we wanted to above the horizontal. So this is a horizontal direction. Could also say 58 degrees if you wanted in the northeastward direction. That would be fine too. North of east would be okay. All right, so those are our two practice problems. Now, your assignment today, assignment part 1, we have that computer lab. It's that effect simulation again that we did. There's a link to go to it directly. You'll be using these formulas on that assignment as well. But we do have this in-class practice that we did following the notes. So some problems that we did on our own here. Answers are next to the problem, so you can check your work that way. So here we have Tarzan, who swings west 30 meters and lands on a tree that he then climbs up 8 meters. What was his resultant displacement, and at what angle was his displacement? So I did draw the first little bit just to help you all out here. So we're first going to draw a picture. So if he's going west first, so I'm going to go wherever the westward direction would be if I was treating this like a compass. So west first, then connecting tip to tail, going up a tree. So up is going to be the vertical direction, and so I can draw my arrow pointing upward as if like I was pointing toward the north here if I wanted. And so I want to figure out then how far it took him to go from here to here. So dx is how far did he go horizontally. So that's 30. That's what's the horizontal, that westward direction. And then notice this angle is touching 30, so that's the adjacent leg of the triangle. That's adjacent or next to the angle. And then dy is 8, and that's opposite the angle, so that's going to be my opposite triangle leg. And I'm trying to find resultant displacement and angle of displacement again, so that's my two unknowns. And so that equation, so same one that we did before, so dx squared plus dy squared, we're going to take then the square root of that over inverse tan of the opposite over adjacent leg of my triangle. So we're going to go ahead and sub this in. So 30 meters squared plus 8 meters squared. So we should get 31 meters after solving for that. And then For theta, the inverse tan of the opposite over the adjacent leg. So 30 meters over 8.0 meters. Take the inverse tan of that. And so we should have 15 degrees as my angle. And then you can include a description for that. So 15 degrees above the horizontal would be fine. Or if you wanted to do northwest, that would be fine. But either of those would work for your description here. So try the rest out. We got 2, 3, and 4 here. 4 is probably the trickiest one. I do have a little help visual for you for 4 that's attached to this. So you can kind of check your drawing. The big thing here is just making sure you have the drawing done correctly. So there is attached some homework help, or I guess work help for 4 there. Aside from that, please send me an email if you have any questions, and I will answer it as soon as I can. Hope you're all doing well, and I'll talk to you later. Have a good day.